Okay, so for Christmas, my son wanted a blue laser so he could burn some things, and we thought, oh, that'd be kind of fun. I thought it would be fascinating too, but realized it was pretty dangerous. So we purchased a blue laser that had a wavelength of 405 nanometers. Okay, so let's calculate how much energy is given by one photon from that blue laser. For that, we will need this equation, which is E equals H nu. And where E is energy, and in this case it's going to be in joules, and H is Planck's constant, Planck constant, and Planck's constant is 6.626 times 10 to the negative 34 joules seconds. That is joules times seconds, not joules per second. And of course, frequency is given in per seconds, and you can see that those units would actually cancel each other out. But the problem is this laser was given in wavelength instead. Nanometers is actually wavelengths. So I need to convert that over. Now, we know that from previously that speed of the particle, c is equal to lambda times frequency, lambda nu. And if we rearrange that, we can solve for nu by dividing each side by lambda. And so what we wind up with is c over lambda is equal to nu. So we can actually just substitute that in for frequency. Our frequency is given in nanometers, but we've got to change that over to meters because the speed of light is given in meters per second, where c, of course, is the speed of light, 3.00. Well, that was a sloppy way to write that. 3.00 times 10 to the 8th meters per second. So we've got to make sure all of our units are in the right form. So I'm going to go down here to the bottom. I'm going to convert 405 nanometers by just doing a dimensional analysis. I put nanometers on the bottom and meters on the top. And I know that nanometers is smaller, so I'm going to have a lot of them. So I have 1 meter is equal to 10 to the 9th nanometers, which would give us, we cancel those units out, we wind up with meters, so we get 405 times 10 to the negative 9 meters. You see, the 10 to the 9th is on the bottom, so you get a negative number. But that's not proper scientific notation. We need to move that decimal place over 2, so that's going to be 4.05 times 10 to the negative 7 meters. So that is our wavelength in meters. And so that is equal to our new part of the equation. Now we can go ahead and do our calculation. So energy is equal to Planck's constant, which is H, 6.626 times 10 to the negative 34th joules seconds, times the speed of light, 3.00 times 10 to the 8th meters per second, over the wavelength, which is 4.05 times 10 to the negative 7 meters. I'm going to pause this while I grab a calculator real quick. Well, I went to grab a calculator, a scientific calculator, and it turns out Ms. Hurt has the only one in her house right now. So I'm just going to do this the old-fashioned way. I'm going to do the coefficients first, which would be, because I'm using just the calculator that's built in on my computer, 6.626, and then I'm going to multiply that times 3, and then I'm going to divide that by 4.05, and I will get 4.91. All right, so I know that that's going to be my start. I've got 3 significant figures. So I've got negative 34, and to that I'm going to add 8. And then I'm going to also add 7, because that's a negative and it's on the bottom. Then we're going to wind up adding it. So negative 34 plus 15, and I get 19. So that's going to be times 10 to the negative 19 joules. Notice it's joules because the per seconds cancel out with the per sec. Joules seconds times per seconds cancel out. And then we've got meters divided by meters, and so that cancels out. So we wind up with just joules.